Welcome to this lecture of discrete time Fourier analysis part 2. In this lecture we will discuss about DFT and its applications. First we discuss DSP components, that means digital signal processing basic components in this particular lecture. Then we consider spectrum domain sampling, which is the fundamental idea behind DFT computations, how basically DFT analysis equation can be computed in computers, and then we will look into one example, application example. This is the complete scenario of DSP components. As you can see that input input is xt, which is analog continuous signal, takes into anti-aliasing filter, which is basically an analog filter which limits the bandwidth of the input signal xt so that we can fix a sampling frequency value. Then it passes through sample hold circuit and produces analog discrete time signals. Then it feed to a quantizer to convert this analog discrete signal to its digital discrete form so that it can be processed directly within a DSP systems, where the different algorithms of DSP filters or DSP systems are basically carried out. Then after processing, it produce first of all a digital discrete category signal. Then it takes into the decoder circuit. Decoder produce y of n, which is our main interest of this subject course. This can be considered in two different domains rather. One is analog discrete, which is basically the ideal conditions which we deal in our numerical problems, in theory problems, theoretical paper problems. But in practice, this decoder basically we place digital to analog converter, so the output will be staircase approximated output. So the category should be analog continuous, not exactly analog discrete. It should be, in practice, it should be analog continuous. To smooth the staircase output, different kind of filter which is called a smoothing filter is used to produce the final analog continuous signals. It's something like that. And this particular shaded block is actually the DSP based system, where all the signals are in digital discrete domain, and this is basically digital processors. Most of the introductory DSP courses deal with analog continuous signals, either in the form of analog continuous signals or analog discrete signal as an input. It takes into DSP algorithms to produce either of the forms, analog continuous, likewise your computer generated sound directly reproduced through a speaker, that is analog continuous, or in theory papers we solve numerical problems in the form of analog discrete, that is yn, already we had seen in earlier presentations, and digital discrete form which can be stored back to digital memory systems. Now the main course objective is to deal with these two categorical signals at the input, analog continuous, analog discrete, as we already talked about, and to develop the DSP algorithm based on the fundamental mathematical formulations, which also considers the user specification as one of the input, and final output should be in a analog discrete domain. Now just consider the problem we had seen during DTFT numerical problems, that x of n is a input signal which is in the form of analog discrete signal form, and the system LTI system described by this difference equation, which basically implements the DSP algorithms, and y of n is a final output which is in the form of analog discrete. It could also be possible that input directly given in xt, that means analog continuous domain, and after sampling we could have analog discrete domain input. Now in case of real-time input output signals, what would be the DSP blocks? Most of the Natural input signals are analog continuous domain. It directly takes into the DSP based systems where input, sample hold circuit, quantizer means completely that is called analog to digital converter, and etc. are being considered within the DSP based system itself. It can generally have two different kinds of signal output for applications. Either it is analog continuous or it is digital discrete. If we now consider a real practical problem where input mic takes analog continuous signals, feed directly to the DSP based systems and reproduce the process output through a speaker, that is analog continuous, or it could be stored in digital memory systems after processing for further analysis. Now in this situation, what should be your DSP based systems? Your DSP generally can have your own computer. It can be ARM based processor which includes DSP architecture within it. It can be your conventional Raspberry Pi, it can be Arduino, but most of the audio for audio applications, this Arduino is not a suitable one. This can be used for any robotic kind of applications, but still these are being systems which can be used as a DSP based system. So input can have different form. It can be directly coming from digital storage devices like your mobile memory card, computer hard disks, and this passes through a DSP based systems, means your mobile itself, it can work with DSP based systems. Suppose you are playing a song, so the song is stored in digital memory card. It takes into the mobile primary memories to process the data through equalizations and reproduce the sound as an analog continuous one, which you can listen through your earphones or headphones. So it can also be, after process, can be stored in digital discrete domain in a digital system as well. Now we will revisit time domain sampling. What is time domain sampling? That it tells that input is analog continuous. It passes through time domain sampling process with a specified sampling frequency and gives output sequence, discrete sampling values. Now question is, why do I need this time domain sampling? Just consider one example. Let's say input signal is a duration of 1 second. So within 1 second there are infinite number of points, which is not feasible to store in computers. But if we sample the signal, let's say sampling frequency 1000 Hz. Now we are considering that input signal is band limited such a way, so 1000 sampling frequency is sufficient enough to keep storing all the frequency component without frequency domain aliasing. So after sampling this 1 second of continuous time signal durations with a sampling frequency 1000 Hz, it again remains 1 second duration in discrete time signal, but it contains only finite number of sample point, that is 1000 sample points. Now it is feasible to store in digital hardwares. So this is the main reason of time domain sampling. Now the same concept we apply for storing the digital signal spectrum. How is it possible? Let's take a look of DTFT spectrum. DTFT spectrum is continuous as well as it is periodic over twice pi range. So that's why we draw one fundamental period, 0 to 2 pi. Now the problem is that how do I store this spectral structure, spectral shape in my computer for further analysis? The problem is remaining the same. What to do? Basically we have to sample this particular spectrum so that it can be sampled to a finite number of points, so that it can be stored in computers. So that's why we sample this continuous time spectrum to produce a discrete spectrum. So we did frequency domain sampling. So after frequency domain sampling, this continuous spectra takes a discrete form, and this is the spectrum of DFT, discrete Fourier transform. So the relation between DFT and DTFT is that DTFT and DFT are basically the same, where DTFT is a continuous spectrum and its sample version is DFT spectrum, where this omega k is the discrete radian per sample frequencies which are associated to each k values in the discrete domain, and k is the frequency bin index in the DFT spectrum, where omega k is the associated radian per sample frequency value in the DTFT spectrum. So this is the fundamental or underlying idea of DFTs. DFT is basically discrete spectra of DTFT. The question is that how do I compute DFT directly from the signal sequence? So this is the equation. The equation is called analysis equation, where xn is the input sequence of finite duration, n number of samples. Output is a discrete sequence, again a discrete sequence of n number of samples in the spectrum domain, and xk is called DFT spectrum. Similarly, if we take xk as the input of the inverse DFT, it produces x of n, the original sequence, n number of sample points in there, and the equation is called synthesis equation. Now this is a practical situation that most of the times we encounter a very long data sequence at the input to the DFT, we require to compute the spectrum of a very long sequence of data. What essentially is done? The number one option is that we can take the complete data sequence or data lengths, feed it to DFT analyzer block and get the associated spectrum. That is one option. But in practice, we used different option. What is that option? The complete data is basically framed into multiple sections. This is first frame, this is second frame, third frame, dot dot dot, last frame, final frame. So all the frames, data samples are again finite length, but this is very much smaller than the complete data frame. The complete data length is very large, where L is very small compared to this complete data length. Now individual frames DFT is now computed. So these are the DFT of individual small frames. So this is another technique. The benefit is that the second option has many benefits. Number one is that it can track the spectral changes with time. What is this? If we take the whole sequence at once and put it inside the DFT, compute the DFT spectrum, that would give me a overall spectral scenario of the data. But if we frame it into multiple sections, we can do analysis of multiple spectrum and predict about the frequency variation over the small period. Second thing is that if we frame into smaller sections, we can tackle the computational complexity. That is the system aspect. We'll see later on. Now endpoint DFT. What's its meaning? Let's consider input data length is L and we have a DFT analyzer block of endpoint. That means this particular endpoint DFT analyzer block is expecting a complete frame as an input whose length is also capital N. But now, to avoid time domain aliasing, the rule is number of input data points should be at most equals to, or it can be less than the number of DFT points. So if it is so, if we consider L equals to 5 and capital N equals to 8, so we have 3 sample points to be we have to append 3 additional sample points to this data frame, so that it would be ready to fit to the DFT analyzer block. Now the technique by which we can do that is called zero padding. So where to pad? At the end of the data. And what to pad? Only zeros, so that it can't contribute anything else. 0 means 0 into something is equal to 0, so it is not introducing anything else. So what it effectively does, it basically adjusts the spectral resolution. Zero padding technique can adjust spectral resolutions, and the resolution is measured in terms of delta F. What is this delta F? Delta F equals to sampling frequency in Hertz divided by number of sample points in the spectral sampling. So if we just go back to the slide of spectral sampling, what is delta F? Delta F is the amount in Hertz which corresponds to this particular small distance in discrete spectrum. That means if we increase k value by 1 or decrease the k value by 1, how much frequency shift in the Hertz scale? That is called delta f. So as you can see from here that the duration is fixed. This is 0 means in hertz scale this is 0 hertz. In omega scale this is twice pi radian per sample, means in hertz scale this is sampling frequency. So if we introduce more numbers, that is if we use higher values of capital N, these sample points will become closer to each other, and that would give me a better approximation of the spectrum. And as the distance between these 2 points in hertz scale decreases, it calls higher resolution in the spectrum. That means resolution higher means the value of delta f is low. So now if we consider the example for this specific numerical case, that signal frame length equals to 5, required frequency resolution is 50 Hz, sampling frequency is 400. So what would be the value of capital N? So capital N is that delta f we require to be 50 Hz, sampling frequency 400. So if we cross multiply and do calculation for N, it would come out to be 8. So this is the example. 8-point DFT is considered, and while the input is 5 number of sample points, so we have to append additional 3 zeros at the end of the data frame, so that it is now ready as 8 sample point data to fit into the 8-point DFT analysis block. Another property is that xk is the DFT coefficients for k equals to for kth bin is equals to n times the DTFS coefficient. Ck is the DTFS coefficient associated to kth bin index. In point DFT, it's windowing technique. So we talked about zero padding earlier. Now what is windowing technique? Windowing technique is basically a technique where the original input data is before zero padding or before passing to the endpoint DFT, it passes through a window, specific kind of window. So if you don't use any kind of window, means effectively you are using window technique, that is called rectangular window. And there are different varieties of window, maybe that is they are called as a Hamming window, Henning windows, triangular or Bartlett windows, Blackman window, Kaiser windows. So these are specially used to control the spectral leakage. We will see in a moment what is called spectral leakage. Twiddle factor. Again we start with the analysis equation of DFT. Here we are considering W suffix capital N, which is e to the power minus j twice pi by n. So if we just put this omega n in place of this particular kernel function parameter, so it takes a very compact notation, compact equation, where W suffix n is called twiddle factor. For 8-point DFT, capital N equals to 8, so twiddle factor is represented by W suffix 8 and its value is this. So for different k values or exponent values, this is the table which shows the exponent of twiddle factors. There are two important relation. One is called periodicity property and symmetry property, which are associated to k value equals to k plus capital N and k value equals to k plus n by 2. If you do calculations for omegas considering these k values, you will come out to this final row as output. Now DFT computations, it can be computed through a linear transformation, or essentially it is basically computed in computer programming through a linear transformation method. What is it? We again writing this starting with analysis equation, then taking the form of x of k for any general values of k. It takes a form like this. For k equals to 0, it is the first equation. For k equals to 1 is the second one. For k equals to 2, this is third one. For k equals to n minus 1, this is the final one. So now if we consider the whole set of equation, we can say this is a set of linear equations where left hand side all the components are DFT coefficients and the right hand side is a linear combination of the sequence or the input sequence. So that's why this can be formed as a matrix equation where xk is a column vector and small x basically another column vectors which comes in the right side and this comes in the left side, where this is the transformation matrix W suffix n, its size is n by n, it is a square matrix, and this is called transformation matrix for DFT. Now if we just look into detail of the transformation matrix, it has a special architecture. The first row all elements are 1, first column all elements are 1, and in between the elements are filled from this linear combination coefficients which are being given in this particular set of equation. Now IDFT, inverse DFT. This is the equation already we derived. So if we just take the inverse of this matrix and pre-multiply with this particular matrix to both the sides, we will come out to this expression, and from the synthesis equation it can be shown xn equals to 1 upon n, and if we just if we expand all these components here, then we can compare. We will find out the inverse of the forward transformation matrix is equals to 1 upon n times the complex conjugate of the forward transformation matrix, and if we cross multiply, we will find out that, sorry, if we just take its multiplications both sides, we will find out Wn and Wn star is equals to n times the identity matrix. Now DFT spectrum, there are a few different kind of spectrum which can be computed. It is amplitude spectrum. AK is amplitude spectrum for pin index k. It is basically 1 by n times square root of this individual square terms, where real xk is basically xk is the DFT coefficients for k bin index value k. Its real part is the real xk. And similarly power spectrum is completed, is basically the squaring of the amplitude spectrum, and this is the phase spectrum. And final term is the DC term. DC term is a single one term which associated to k equals to 0. It is basically k equals to 0 means x of 0 divided by capital N. This is called DC term or DC component. Now computational complexity. If we just go back, okay, just let me explain what the two curves explaining here represents here. X-axis, it represents the number of DFT points, and the y-axis it shows the count, and this left figure shows the count for multiplication, right side figure shows a count for addition. If we just consider any one of the equation, let's say this equation, left, so for one bin index, in the right hand side we have a summation of n number of terms. So summation of n number of terms requires n minus 1 number of addition process, and all the individual terms are basically they require some multiplication. So n number of terms requires n number of multiplication process and n minus 1 number of addition process. And how many such coefficients we need to compute? 0 to n minus 1 means n number of coefficients. So total number of multiplication required n square, and total number of addition is required n into n minus 1. This parameter has been plotted. So generally the n values or DFT values are taken in terms of 2 to the power n integer values. So it is 2, 4, 8, 16. You may choose any value as well, no problem. It can be odd, it can be even, there is no issue. But in practice these are standard choice, 2 to the power some integer values due to some specific reason of radix 2 algorithms. We'll talk about much more detail during FFT analysis. And we can see that this is both the curves are following this multiplication count following exactly square, but the addition count is following approximately square in terms. So as the number of DFT coefficient, as the number of DFT points increases, computational complexity increases non-linearly. So it's a huge computational complexity. So now if we just go back and try to re-explain the term which was here to tackle complexity, that means why we did smaller frame. One of the reason was tackle complexity. Smaller frame means number of sample points are less. So number of sample points are less means we are supposed to use a less number of DFT coefficient, computational coefficients machines. So that requires less complexity. So to avoid to a very high computational complexity, we have to reduce the number of sample points in the DFT computation. Now, an application. Let's say that you are given an input signal which consists of multiple frequency component, pure tone, multiple harmonics you can say. One of the example is the DTMF, dual tone multi-frequency, where two different distinct tones are get added to produce the signals, which are used in telephonic keypads. And now you have to develop a system which can predict dominant harmonics, that is a number of dominant harmonics. So if we consider this kind of simple problem, how we can approach just by the knowledge of DFT. The thing is that dominant harmonics means we have to find out the spectrum. We have to find out the frequency. And where to find the frequency of the signal? This is in time domain. Where to find out the frequency? Frequency could be found out from the spectrum. So we need the spectrum. And what kind of system? System should be your digital computers or computer-like devices. So that discretized signal should have to be passed through a particular system which can find out the spectrum of the signal itself at the beginning. So now this could be the one of the solution, one of the process to get the solution. Input signal passes through a DFT analyzer block. It gives me the DFT spectrum. Then we will use Finepix block, where user can control the threshold to find the peaks, and then it can predict the number of peaks. So now if we just go and try to find a live demo of it, this is the program ready for these demonstrations. So for the timing, we are first considering the frequencies 1020, 2076, 5000, 6500. These four are the frequencies which are basically forming the input signal. That's why it is called multi-tone signals. And we are basically using Windows method. That is, where is that window? This slide. This window techniques we are using because we wish to reduce the spectral leakage. I'll show you if we avoid window techniques what happens. And the threshold, the input threshold, as we have seen that user can provide the input threshold. That can be the options. You can make it automatic as well. So this one, and resolution fold, I'm not controlling resolution from here. This is as it is required. You can increase it as well. So now if you run this, what happens? And the sampling frequency is 16 kilohertz here for this process. This is the input signal, what exactly presented in your presentation slide. And this is the DFT output block. There are 4 components we can see, and this is pretty simple to identify the peaks, and that's why we can find the 4 peaks from there. We set a threshold of 0.1, and if it is something more than that, we will be with a certain criteria, we will find out these are the peaks. So that is not so we are not describing what is the way of finding the peaks here, exactly what should be the peak finder location, peak finder algorithm, etc. These are different topic. So now if I close it and try to do some modifications, that I'm going to use this one as a false. This is false. That means I'm avoiding this window block, just taking the data and passing through the DFTs. So what happened? And threshold is as it is. We kept it as it is. If we run, we can see there is a mistake. Okay. See, the spectrum has some kind of ripples, which are unwanted ripples introduced in the spectrum. But in fact, actually in the input signal we consider only 4 frequencies, 1, 2, 3, 4. But it shows, the spectrum shows that there are some another frequency component which are having non-zero effects. But this is not actually the true things. So these are false. These are false. And what it could produce at the output, that means they are basically triggering falsely some of the peaks which are not exactly present, which are not exactly the dominant frequencies. That means these are falsely triggered due to this spectral error, where the error introduced during your DFT computation. So how can I control? Even in these particular situations, I could have used little more higher threshold values. If I do that, instead of this, if I can get rid of this false trigger conditions. That means we have still 4 fundamental dominant frequencies showing, even we are not using any kind of window techniques. So this is the advantage of window technique, as already we stated, that window technique can reduce the spectral leakage. So now if we just come back to the presentation, so this is the actual application. It is a very simple application, just only one application we considered. There are many applications are available in practice, so you may consider any one of it and you may implement. So that's it for DFT presentations. In the next topic we will consider about DFT, its associated time domain signal time domain operations, circular convolution, one of the important topic, and the DFT, how it is related to LTI system output. Thank you very much.